Hello, everyone. Today we're going to spend time looking at the eraser, looking at this piece of the angular momentum torque equation. So the piece I just highlighted is called torque, and we derive kind of backwards because the this last equation, the one I'm pointing to, is more fundamental than Newton's second law, but we can kind of show you how we get there. So if we take our point body and allow it to spin around an axis, and that axis has an R, we'll just call it R axis for now. And what we want to do is we want to multiply both sides of F equals ma by this R axis term. And I'm going to write this as dp dt instead of ma. Alrighty. We will get to the definition of angular momentum, which is essentially how torque makes an object spin. We'll get to it later. But for now, we're going to set it equal to 0, or at least acknowledging that it exists, and we're not going to deal with it. We're just going to deal with torque today. Another important feature of this equation is I'm using something called the cross product to multiply these terms together. And that's another form of vector multiplication, but rather than returning a number, this one's going to return another vector. We use it because we're less interested in the output, like we would with the dot product, and more interested in the direction of the rotation that's going to be caused. And the cross product inherently builds in that piece of the puzzle. Okay, so torque is just equal to R cross F. What good is it? What good is it? Well, let's take something that's rotating around an axis. So that's our axis. And then we push on it. Let's make this force 1. Let's just call this object for what it is. It's a door. So you can do these experiments at home. You can push on the side of the door where the hinges are, and the door is difficult to open. You have to apply an awful lot of force. Yet, if you push where the doorknob is, it takes less effort. Same massed object, same moment of inertia, but pushing is easier. And that's because with F2, you have created a larger force due to the distance between the axis and where the force is applied. You've increased this R value when you push with the outer door, which means you create a larger torque just because we multiply the distance from the axis to where the force acts. Another fun thing you can do while monkeying around with a door, because you're under quarantine orders and things are getting a little bored, is you can push on this door this way with F3. You'll notice that even though you have the same R, F3 has no effect. Well, the door is going to wiggle a little bit side to side because it's difficult to press perpendicularly perfectly. And with that, we recognize that part of what the cross product brings in is a sense of the angle matters. All right, so if we push on the door from the outside, hitting the same point, with F4, combining what we learned with F2 and F3, that perpendicular matters, that's how we want to label the force. We want to have a force that's perpendicular to the door, which we know, like F2, will have a great effect. And we want to decompose it into a force that's parallel. And the force that's parallel is useless. So when you apply F4, you only really care about the perpendicular component. That's what's going to give you action. So it's like decomposing any vector we've decomposed so far, only rather than worrying about x and y, we're paying attention to how the door is going to rotate and its axis. Let's see. As a definition, RA is called the moment arm. It's just a term that predates our understanding of torque, I'm sure, but is used frequently in engineering. That you talk about, say if you have a let's see, six-sided. So you have a bolt. So this is the stuck bolt analogy. And on that stuck bolt, you put a wrench. And that wrench has a, from the bolt to the end of the length of the wrench, this would be our moment arm. This is R around the axis, which is our stuck bolt. What you do to break it open is you apply a force. And you usually do this somewhere near the end of the wrench. But there's really only so much force that you as a person can apply. So what people do is, in order to increase the torque, they increase the length. Something effectively known as a cheater bar. And you just put a piece of pipe around the end of the wrench, and that extra length produces more torque. Okay. And of course, you always do your best to push perpendicular with the wrench, but sometimes you got to push in so it doesn't slide off. Watch your knuckles. Yeah. Okay. So we talked about breaking down the force vector into components, but there are going to be some times when the object we're dealing with, say, something at an angle where we know this force, for example, what we might want to do is decompose the moment arm. So this is now our parallel, this is now our perpendicular, and our moment arm is the piece of the torque that we decomposed, because with the force there, it may just be easier to draw the perpendicular moment arm. And that just all really depends on the situation. The next thing I wanted to deal with torque was torque and work. So we have our old buddy, well, let's go, our old, very friendly buddy, our old equation involving energy of a system. And that's going to equal work. But what happens if the energy of our system is something like the kinetic energy of rotation? Then we have something that is spinning, but our definition is force dot dr. So this should be a very common occurrence if we had a wheel or a pulley or something. Which is feeling a force this way. It's a good example of a problem because center of mass is in the middle of the wheel and there's no dr. The force pulls off this wrapped string. It'll come off always perpendicular. So where's the movement? Well, dr in this case is the force distance. So how How much distance did the force travel through? Another scenario, I'll pop above it, is if we again had a easy to rotate object. So let's say something like an asteroid, and we apply rocket thrusters right at this edge. We know wherever the center of mass is how it's going to rotate. So this would be our R. R from the axis. All right. But what this force is going to do is this force is going to cause this asteroid to rotate. As well as move. It's going to rotate, and it's going to have a standard velocity this way as the force causes the center of mass to accelerate. So we'd like to be able to talk about this in terms of energy. And that's where we're back with F dot dr. So first, for both of these pictures, you can take a generic torque that has a vector is equal to R cross F. And since these pictures are in the XY plane, the torque itself needs to be perpendicular. We don't necessarily care which way, but it does need to be perpendicular. So we get R, F, and we get Z hat, and it's perpendicular to Z. Or Z if you're from Canada. All right. So we need to substitute in our force into this mess because, after all, that's what work is looking for. It's looking for a force to be applied. So, again, work is integral F dot dr. And let me bring in for F that strictly, so the F is equal to our torque divided by R. And our R is just carrying a magnitude right now. And then that force is going to be carried over a distance. So when I'm rotating an object, any object, let's take it apart. So from the center of mass, the force is rotating with the object. So it does this. Same force, different locations. And most importantly is this piece of the puzzle right here, because this is delta x. This is how far the force has to travel. Sorry about that quick error. That should be delta R. Delta R. Each of these are R's. We've seen before that this delta R then is equal to the change in the angle times R. This is just the arc length. And if we go back to our work earlier, it's what leads to things like V equals R omega and other useful rotational terms. So the force is going to travel over a particular arc length. So delta R, dr, becomes the change in theta times R. Our R's will cancel, and we wind up with the work that's associated with rotation is equal to the integral of the torque dotted into d theta, which will also have an angle, which we'll talk about when we in the cross product lesson. So all told, if you want to change the rotational kinetic energy, you need to do work on that in a way that rotates. And that's an important way that torque figures into our equations. We're going to keep talking about torque. We've got a couple good examples to do. And so tune into part 2.